This clip is part of chapter 5 of the theory of structure. We are discuss about the cable. The cable is a structural member that is flexible, inextensible. It can resist the force by developing tension in sizes. The cable that we are studying is the statically determinate cable. That means we can analyze the cable by using the method of section, method of joints to obtain the reaction, to obtain the force in the cable. And the cable will have the maximum tension force in itself, and most of the time the maximum force occurs when the cable have the maximum angle with the horizontal line. In addition, if you may recall, the horizontal force of the cable, they are always equal to F sub h, and that's going to help us to determine the force in the cable by the equation of T cos theta equal to F sub h, and then T is equal to F sub h divided by cosine theta. If we find the theta, so we just input into this equation, we can find the tension in the cable anywhere of x. Now, we come to another structure member that is in opposite or reverse to the cable. It is the arch. So when it's in reverse of the cable, the arch resists the external force by developing the internal compressive force. That means the arch must be stiff. Unlike the cable, when the force put the cable in tension, if we draw the free body diagram, okay, that's going to produce elongation. So the cable have stability by the tensile force. For the member in compression, as we may recall for chapter 13, the buckling of the column, the 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 member that's in compression is prone to the buckling. So when we design this kind of structure, that structure must be stiff enough to prevent the buckling of the member. Okay, and there are a number of arch. Arch may be parabolic arch, maybe circular arch, maybe triangular arch. That is most of the arch we are studying here. And this arch, unlike the parabolic arch, will have the internal shear, internal bending with the compressive force. Okay, only the parabolic arch that is good. That's going to have only the compressive force, and we will prove it later. Okay, thinking about this arch, by the construction of this bridge arch, we may see that the force from the bridge will act to the arch like this. So the arch will provide the resistance force, the reaction in the vertical direction, and also it will provide the inward horizontal force to resist the action of the applied forces. It is in the opposite of the cable. Okay, the cable, when it's subjected to the force, it will develop the upward force and point out force, but the arch will have the point in reaction and also the same upward reaction. And also for this one, this bridge also have its own force acting on it due to the dead load of the bridge and also due to the life load of the people who walk across this bridge. And then the reaction of this gonna be like this. Okay. Uh, there are two big type of arch. One is the statically determinate arch. Another one is statically indeterminate arch. First, we take a look at the fixed arch. Under the action of the force, you may see this support will develop the three unknown reaction and moment. And this arch will have the unknowns of 6. And since there are going to be only one piece of arch, okay, so the number of n is 1, and then we have 3 equation of equilibrium. So that means this structure is statically determinate with degree of indeterminacy of 6 minus 3 is equal to 3. And next, if we have two hinges arch. Hinges mean this, they call it hinge. Actually, we call it pin, but technical term for the arch called it hinge. Under application of the force, again, this hinge or pin gonna resist the force by the reaction of this. That means this going to have the unknowns equal to 4. And since the arch is going to be only continuous arch, and we have 3 equation of equilibrium, okay, this going to be the statically indeterminate arch with the degree of indeterminacy of 4 minus 3 is 1. And then we have the 3 hinge arch. This means it has one hinge here, one hinge here, and one hinge here. Again, the reaction here is going to be 2, horizontal and vertical. And since it's the hinge going to have 2 internal forces also, because the hinge cannot resist the moment. So if we consider the hinge arch, if we consider the hinge arch to be 2 parts, we have the unknown equal to 6, and for the degree of freedom we have 2 parts of it and times 3 equation of equilibrium. So this 3 hinge arch is a kind of statically determinate arch, okay, and the other NA and B is statically indeterminate arch. The Thai arch also, that we can determine the reaction of the Thai arch easily. We have it subject to some kind of force, and then we have only 3 unknown forces. So you just use the equation of equilibrium. However, if you cut this arch, okay, by this section, you see, you will have 4 unknown, and you cannot solve it. You can only determine the reactions of the Thai arch, and the degree of indeterminacy of this is going to be 1. Okay, and in conclusion, we can only solve for the 3 hinge arch following the arch shown in this one. Okay, and there are some examples here. There is an arch shown over here that link between 2 big building apartment. Here, this is in China, and also this bridge in Chengdu, that is cross one part to another part. It support the traffic surface between this point and this point. Okay. For this arch has parabolic shape, and if it's subjected to uniformly distributed load W, the internal forces developed in this arch going to be only compressive force. This is due to the levers with the cable that have also the parabolic shape and subjected also the distributed load. And for myself, I like the arch with parabolic shape because arch with parabolic shape is in the shape that is kind of not too dub too much like a circular arch or even the cantilever arch. And most of the arch that I see in the bridges in the America is have a shape like a parabolic arch. We will discuss this later in the example. Okay, if you have the parabolic arch, you're going to set the origin of the coordinate xy at the cloud. This is called the cloud, the highest point of 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 the arch. Because this is the cloud, CROWN. Okay, we set these points at the origin of the xy axis, and following the same distributed load, it's just the levers of the cable. I'm talking about the arch with the parabolic shape. The shape is going to be like a black line here. If it's the circular, okay, it's going to have the shape like the pink line. If it have the cantilever, if you recall cantilever is the shape of cable when it's subjected to its own weight. The cantilever is in between the parabolic and circular arch. And anyway, like I said, I like the line of parabolic arch better than the other. Okay, we arrive at Ting arch. The Ting arch is a kind of statically determinate structure, as I did mention before. And when we saw this problem, we got to separate the arch into two pieces. For this, you may have the force at the A and the force at the C. And then if you put the BC part and follow the third law of Newton, the force at the hinge gonna have the same magnitude but in opposite direction. So now we have the total of 2, 4, and 6 unknown. When we solve this, which way we are going to use? Each equation you will have 3 equations of equilibrium, and most of the time we take the moment. And how do we take the moment to obtain these 6 unknown? One of the best way is just take the moment about A to eliminate the A sub x and A sub y, and then get the equation of C sub x and C sub y. And second, you take the moment over here to eliminate B sub x and B sub y to get the equation of C sub y and C sub x. So by doing this, you're going to get 2 equations, okay, and to solve for 2 unknown of what? Of C sub x and C sub y by solving the simultaneous equation, okay. And then we come to the example that I just mentioned about the parabolic arch that I like its shape, okay. When we have the parabolic arch, we should take a look at its first, and all the time as we discussed, the origin of the coordinate xy must be at the cloud of of the arch. And then following the equation that we have is going to be y equal to h. What is going to be the h? H used to be the set, okay, of the cable, but this time H is going to be the crown length, okay, between the foundation and the crown of the arch, and that means this is going to be 12.5. And then the L is going to be the length between this portion, okay, and that is going to be 25 square. Well, it's not the total span of the arch. It's going to be the part that we are interested in, and then x square. And it's going to have the negative, okay, before it, because the y going to be below the x-axis, and all of the y is going to be in negative value, okay. And they are going to ask us to determine the internal forces and bending moment at any x from the origin. That means if you said this is going to be the x, we're going to put this is going to be the x, and this is going to be the y, and the y is going to follow this equation, minus 12.5 divided by L square x square. And then you also can determine the slope of this equation, okay. This is slope, and you may recall that this slope is also going to be tan theta. It's going to be the angle at any point of x, okay. Now we start by finding the reaction of the arch, and before finding the reaction of arch, just draw the free body diagram. Just take the support out, and you can have a sub x and a sub y, c sub x and c sub y. And like I mentioned, the c sub x for this always point into this, because the arch gonna try to move outward, try to move in this direction. When you press this, when you press it down, it's trying to move this way, it's trying to move this way, and that's why the reaction gonna be in the opposite direction. Okay, let me erase this. Okay, next, what do we have? We're going to have the need to use the equation of equilibrium. Just take the moment at A. Okay, that means we're going to determine the c sub y, because the line of action of c sub x is gonna cut this point, and that means we're going to have only one unknown, and c sub y gonna rotate what in this direction, and you also have the resultant force here is going to move in the opposite direction, so the balance of the moment will occur, okay. And then let me set this rotation is plus, so c sub y times what? c sub y gonna times this 50 meter, and the resultant force gonna times this half length, so you got this c sub y times 50, and the resultant the line of action is here, so times 25, you get c sub y of 250 kilonewton. And then you may have summation of f sub y equal to 0, and upwards is plus. You will have a sub y plus 250. That's going to be equal to 10 times 50. So you got the a sub y of 250 kilonewton. Okay, and the a sub x we cannot find from this free body diagram. You got to draw another free body diagram, which is half of the task. If you put half of the task, that means you're going to have the b sub x and b sub y here. Okay, and now you have what? You have 3 unknown, and the best way to solve this free body diagram, you just take a moment about B, and then the 250 kilonewton gonna rotate in this direction, and this one gonna rotate in this direction. And that's mean what? That mean the 250 kilonewton gonna time this 25 kilonewton, and the C sub x gonna time this, which is 12.5 kilonewton. If we have that, and then we put the moment at B, and we put this as the plus, so the C sub x times 12.5 is positive, and then the 250 times 25 is going to be negative. And we also have this is the resultant force of the uniform load. That is going to rotate with the same direction as the C sub x. So it's going to be 10 times 25 and have the moment arm of 12.5. And then you put it in your calculator, you get C sub x of 250 kilonewton. When you get this for 250 kilonewton, okay, you get this 250 kilonewton. You may find the B sub x and B sub y. By summation of x sub x equal to 0, you get B sub x of 250 kilonewton. And if you do the summation of f sub y equal to 0, you get what? B sub y is up 1. This is up 1. You got B sub y plus 250. Plus 250, and then this one minus 10 times 25, so it's going to be 0, and then B sub y is 0, as you may see. Okay, so it's similar to the cable. Remember, at the minimum point of the cable there is only horizontal force, and this is at the highest point of the arch, there is no vertical force. We have only the B sub x, okay, and B sub x is going to be horizontal force, and you may notice that B sub x is equal to C sub x, since there is no lateral force acting on it. Okay, next we will use the method of section to cut the frame into the section at what? At the point D, as they like to say. At this point D, we have the horizontal of x, and we have the vertical as defined by the parabolic arch. So cut it here, project this into here, and then we have this as the y, and the same as this. And as the cut, since the frame, in the arch is a kind of frame, so a cut of arch going to produce the moment, axial force, and shear force. And can we determine the theta? You can determine the theta by dy by dx, and that's going to be tan theta. We will discuss this later. Okay, what to do? Take the moment at D first, and then we follow the direction of M sub D. M sub D is positive, so M sub D is positive here. What we have is this one, the 250. The 250 gonna time y, and it's going to move in the opposite direction. Okay, N sub D and V sub D has 0 moment. And what we have else? This is gonna be what? This is gonna be 10 times x, and the distance here gonna be what? X divided by 2. So this is going to produce the moment with M sub D. So M sub D plus 10x times x divided by 2, and minus what? Minus 250 and times this y, and then you get this equation. You put them together, and you may see this is going to be 10x squared divided by 2. This is 10x squared divided by 2. So this is going to be minus 250, and then x squared divided by 50. So this one is going to be 5. This one is going to be 5. So it's going to be 5x squared and minus 5x squared. So M sub D is 0. That is no moment for the public arch. And we still have n sub d and v sub d. So let me illustrate this one first. Let me start with the consideration of the force in the horizontal direction. Okay, and what we have is, if we project this n sub d into this is going to be n sub d cos theta, and again this is going to be v sub d sine theta. It's going to be to the left, and this one going to be to the right. So we may write the equation like this. 250 is plus because it's follow the sign convention, and the blue and the red have the negative like this. And also, if you project the blue in 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 this direction, you get it upward. If you project this, you're going to get it downward. So what we have is the force like this one, the blue is going to be n sub d sine theta, and this is going to be v sub d cosine theta, and v sub d cosine theta have the same direction of 10 times x and is in opposite direction. So we will have n sub d sine theta minus v sub d cosine theta and minus 10 times x, and then you get this. Now you got to solve these two equations. These are kind of a symbolic equation. If you have the Mathematica, MATLAB, MATCAD, or Maple, you can solve it easily. But by doing this, you use the matrix to do so. And then you may have, if you recall from the matrix, sine v sub d plus cosine n sub d equal to 250. This is v sub d sine plus n sub d cosine equal to 50. Recall that, right? And this is going to be minus cosine v sub d. This is going to be here, and plus sine n sub d plus sine sub d equal to 10x. Okay, and to solve this, you got to inverse this. Okay, put into this, or you may see it's going to be sub d n sub d, and then it's going to be the inverse of this square matrix, and going to time 250 and 10x. How do you inverse this equation? Oh, you find the determinant. Okay, the determinant is what? The determinant is the time of this. Okay, and going to be minus the time of this. So you got this as the determinant of A, and this is going to be the cofactor of A. That means you just switching this one, and then you get this. So you may get the equation of this of v sub d equal to this and n sub d equal to this. And we still don't know actually the value is yet, because it's in the function of theta. How do we do that? We come into the equation of arch, and then we have the dy by dx. If you do the dy by dx, it's going to be differentiate of this, right? And then when you diff of x squared by dx, you get this 2x. Okay, that's it's going to be this, right? And then that's mean by the physical meaning, you're going to have the negative slope. That means if you start here, you're going to put it downward here, and then this is going to be minus x. You don't need to put the sign here because it's already downward, and this is 25. So this one is going to be square root of 25 square plus x square. Okay, next. Yes, if you like to find the sign is going to be what? The sign is going to be the x is different. The x divided by this. The cosine going to be 25 divided by this. And then if you put into this equation, you will get v sub d equal to 0. As we have it before, the parabolic arcs have no shear force and also no bending moment. And the equation for the axial force is in the form like this. And if we like to see the distribution of it, we got to put it, okay, into the graph, and then we can see that the maximum C max is, or A max also gonna occur at this point of 353, and this is going to be the minimum at the crown of the arch, and this is going to be at the support of the arch. And then how do we set the arch? The arch is in compression. You also need to consider the buckling of the arch, okay, especially at the support, because at the support we have the maximum axial force there. So maximum axial force occur at the what? Occur at the arch support. The same as the cable, the maximum tension in the cable occur at the support, right? So let's have the maximum angle between the member and the horizontal line. Okay, let us next consider this Teaching touch arch. Okay, and then we like to determine the reaction at A and reaction at B. This is a pin, but it's going to act like a hinge. There is two forces, and by arranging this, they just cut this member out to make this one the B as a hinge. So we have the hinge here. And then if we draw the shear diagram, if we draw the Fourier diagram, we got the reaction, 4 of them. And then we have 2 more at the hinge at B. So the total of unknown is going to be 6. And you can separate this part into 2 parts. And then we can determine the force SB first. Okay. And we know the force at B by taking the moment at A, you got one equation. Taking moment at C, you got one equation. You solve for B sub x and B sub y. And when you know B sub x and B sub y, you can find A sub x and A sub y. And B and C sub x and C sub y later. Okay, let's draw the free body diagram over here. We have A sub x and A sub y. We have C sub x and C sub y. And at the B, don't forget the magnitude of the force SB. They are equal, but they are in the opposite direction due to the third law of Newton. Okay, so take the moment A first, and you may see if you take the moment at A, this guy B sub x gonna rotate this, and it's gonna time 30. B sub y gonna rotate the same as the B sub x in the counterclockwise direction. Then it's gonna time 40. If both are positive, I mean the counterclockwise is positive, they are going to be this. Okay, and the author we have 300 kilonewton times 10 times this, and it's going to rotate this way. 300 kilonewton and 100 kilonewton going to be here, and also rotate here with the length of 20, and this is going to be 100 times 30. That's all negative. Put this here and here, and then we rearrange the equation. We get the equation here. Okay, next let's take the moment at the C, take it out, and you may see the B sub x also rotate here with what? With this of 30 meter. B sub y now is in opposite direction here. Okay, and gonna time 40. So we're going to have C sub y, we have B sub x as the negative. So and b sub y is the positive. So we said we have this counterclockwise all are positive. And then we also have this one times 20 and plus this one 200 kilonewton times 10 and plus. You have this and equal to 0. You got this equation. Now let's stop the clips and do the practice. What do you get for the b sub x and b sub y? Solving the simultaneous equation. Okay, you got the b sub x of 233 and you got the b sub y of what? Of 25. So this is equal to 233.33 kilonewton b sub x, and the b sub y is 25 kilonewton, and b sub y is 25 kilonewton. That's all we have for the force at the hinge B. And then later we can use the free body diagram to determine the a sub x and a sub y. It's going to be really easy. Summation of x sub x equal to 0, and see all the normal force going to be equal. And if you put it in summation of f sub y equal to 0, the a sub y is upward. Okay, and 25 is upward, so the dr2 is plus, and the other is downward, that's negative. You get the a sub y of 475 kilonewton. And for this, you do the summation of x sub x equal to 0. Again, you may see f sub h is a constant. They are equal in every point. For the f sub y equal to 0, the c sub y is upward. And this guy downward, 425 downward. Okay, and now we arrive at the reaction. And we can see that for the reaction at point A, that we have, and reaction at point C, that we have, you may see the resultant of the reaction as point A going to produce the largest maximum force in the arch, in the tusk arch. Okay, you may put it here and get 529.2, and then we can determine the force in the member of the tusk by following the analysis of determinate tusk. You may use the method of choice, or you may use the method of section. You can try all the forces in the member of the tusk. Okay, and we come to our last example. Is for the Thai arch. Okay, the Thai arch have the have the support A and C. A is the pin, and sorry, that's wrong. This is going to be the C. C is the roller, and then B is going to be the hinge here, the GE hinge here, and since is the A is the pin, so the reaction here going to be a sub x and a sub y, and since the B is roller, so this one only going to have c sub y. And by using the equation of equilibrium, we can determine the reaction of this tusk easily. Okay, let's start. And as you may know, we have three equations of equilibrium, and usually we take the moment at the point of what? At the point of maximum unknown. So take moment here, and you may have this c sub y gonna rotate counterclockwise, and this one gonna rotate what? Clockwise, and this one also going to rotate clockwise. So we have c sub y time what? Time this is going to be 5.5 is if it's positive. The 10 times 4.5 is going to be to negative. and 15.5 is also going to be negative. Okay, you can have c sub y times 5.5 positive, and the answer are negative, and c sub y is 9.545. Okay, this is gonna be equal to 9.545 kilonewton. And then we may do the summation of f sub y equal to 0. Okay, so we determine the a sub y. The a sub y gonna plus this one, and then it's gonna be minus by 15 and 10, and then we get a sub y of 15.45. Okay, we have this one for 0. This is 0. This is going to be 15.45. We are going to find what the force SB. So we got to use the free body diagram of portion AB. Now the free body diagram of portion AB like this, and then at B you're going to have B sub x and B sub y. And if you consider this, what do we have? We have three unknowns: B sub x, B sub y, and t. And you can find the force in the tie lock T by taking the moment at B. Okay, and then you may see the T gonna rotate this way. The 15 also rotate this way. So what we have, they are going to be plus. So the T gonna time what? The T gonna time the distance here is 2 meters. And this guy gonna have the moment arm of this is also 2 meters. But the reaction A sub y is going to time this 2.5 is going to be in the opposite direction. So we have this. The 15.45 is negative times 2.5. And we have T of 4.32. And then we can summation of f sub x equal to 0. So the b sub x that we have in this direction and in the opposite with the T of 4.32 kilonewton. So b sub x is here. And finally, we have the summation of f sub y equal to 0, and then b sub y is downward. Okay, we have the b sub y is downward plus 15, this one, and this one. However, this one is upward. It's going to be 15.45. So b sub y is 0.45 kilonewton. Okay, now we have all of the reaction at A and C, and also the internal force SB and the tie lock. And let us consider this tie arch is in parabolic arch and is follow the arch equation of this, and we set this one of x and this one of y, and this one going to be 0, 0. Okay, and coordinate of point D, let's move this one for minus 2 and put this one here. This one going to be minus 2 and minus y. And then we come here, y is going to be what? Y is going to be minus 2. 2 is what? 2 is the cloud. 2 is the cloud. This is 2. This is the cloud. Okay. And this is going to be 2.5 square is going to L. This is going to be L. This is going to be H. By doing this, you can determine the Y, right? Yes, sure. Just put 2 into this equation. You will get this one as equal to minus 1.28. So we have this as a coordinate. And then we can draw the portion of the arch from A to this. Since this one is 1.28, the rest of this is going to be 2 minus 1.28. That is going to be 0.72. And then we have the reaction here. We have the internal force N, the shear V, the moment here, and also there is the angle. Okay, that's we supposed to determine the slope, and we can diff this equation. Okay, and then it's going to be 2 times 2 is 4, and then it's x. What the x is? X is going to be minus 2. So you get the theta of 52. And then I ask you guys to do your computation to practice your skill on this. And this is going to be the end of the cable for the PowerPoint part. And I will demonstrate you how to solve the problem manually, step by step as before. Okay, that is for this